All right, so now we're going to look at Newton's law of gravity, and this is a more accurate model of gravity, right? So mg is pretty accurate, but only near the surface of the Earth, and actually in this model we'll talk about why that is. Gravity can't go forever, right? If I'm like on the other side of the galaxy, right, the Earth can't pull on me with mg. Like all those planets and stars can't pull on me with an mg, right? It would be impossible for the force to extend forever, right? That's not it doesn't really make physical sense, right? So the reality is as you get further away from the Earth or further away from stars and planets, the gravity does decrease, right? Even though we assumed it was constant mg. Now, the thing is this formula is more accurate, so let's talk about what it involves. The direction of the force of gravity isn't any different. It's always towards the center of the Earth or whatever object causing the gravity. It's just there's a more involved formula when you start getting further and further away from the Earth, and it's given by this formula here. Force of gravity is given by G. G is a universal constant, just a constant to make units match. M1 and M2 are the two masses, right? So, for example, if we're talking about gravity between me and the Earth, one of the masses will be the mass of the Earth, the other would be my mass, okay? And then R is the distance between the center of masses, okay? Now, why is it, before we get into the formulas, why is it that how does this reconcile with mg if we look at mg? Well, if we're standing on the Earth here, right, and this is like me on the Earth, the r isn't zero because the r is the distance between the center of masses. So r is going to refer to the distance between me and the center of the Earth, which is the radius of the Earth. So if I go up, like up and down here on the surface of the Earth, like even from an airplane, like that's a very, very small difference compared to the radius of the Earth, right? Like it's like I'm a little further or like a little closer to the Earth, but still about the distance I am from the center of the Earth is still about the radius of the Earth. It's only when you go really, really high up that now this distance starts to matter, when it's like, now it's not, we're just doing our, like the radius of the Earth. But when we're close to the surface of the Earth, the distance isn't varying that much. Like it's like changing a little bit relative to the size of the radius of the Earth, which is why we can get away with the force of gravity here being equal to mg. But realistically, as you go up, gravity's a little bit less. Like if you climb to the top of Mount Everest, you'll find, and you were to measure gravity accurately, you would find that it's a little bit less than when you're near the ocean level, because you're slightly further away. Very, very small, noticeable. You have to go pretty high up. You're talking about orbits of satellites or space stations before like the gravity is noticeably weaker. Okay. So let's go. The only difference now is that formula. And so let's look at some examples of here. So we have a satellite of mass m is orbiting little m, orbiting a moon of mass capital M at a distance r above the surface of the moon. So the distance here is r. The radius of the moon is r, capital R. Draw a free body diagram of the satellite and compute the force of gravity. Okay, so now we're going to draw the free body diagram. And again, remember, gravity is the only one that doesn't require touching. Nothing is touching the satellite, but there is gravity, and it's pointing towards the center of the moon here, right? So that's going to be given force Fg now. Now this force of gravity Fg is going to be, just write the formula, G m1 m2 over r squared. Now you got to be careful. Don't just use, they gave you an r, doesn't mean that that's the r, right? It's G, the mass of the two objects involved, which is the satellite and the moon, and then the distance between from the center of masses. Well, the distance from here to here is little r, and the distance from here to here is big R. So the distance between their center of masses is little r plus big R squared, like that. Okay, so don't, be careful. Just because they give you an r doesn't mean that that's what you're just going to plug into the formula, okay? You got to remember, this is the distance between the center of masses. Okay, 3 planets are shown in a line as a figure below. Draw a free body diagram for the center planet and find an expression for the net gravitational force. So we're going to draw the free body diagram. Now this planet is going to do a force of gravity, we'll call it Fg3, pulling towards this one. And then this planet is also going to have a force of gravity acting towards it, we'll call it Fg1, pointing that way. Okay? Now they're always pointing towards the center of the other object, so that's why we draw this one pointing towards this center, this one pointing towards this center, right? So it's not always straight up and down. Now we're going to make right positive, and our F net is going to literally be FG3, and I just chose to be right positive. There's nothing special about right, and then FG1's pointing to the left, so that's a minus there. Now this is G, so FG3 is going to be the mass of the two planets here, so it's going to be M2, M3, divided by the distance between their center of masses, which is D, and then FG1 is going to be between these two planets, G, M1, M2, divided by the distance between their center of masses, which is L squared, like that. Okay. Let's do one more example where we have to deal with density. So sometimes problems like to ask about the density of an object, which is the ratio of the mass to volume. Okay. Uniform density means that the density is constant. So density is generally kilograms per cubic meters. It's the ratio of mass to volume. So sometimes we have to think about volumes of objects or volumes of spheres. So consider an unknown planet that has twice the radius of the Earth and the same density as Earth. How does the force of gravity on the unknown planet compare to X? So if we look at force of gravity, it's G, mass of me, mass times the mass of the planet divided by R squared. Now, what they're telling you here is that the radius of the planet is times 2. But you also got to think of what the mass of the planet is going to be, right? Now, because it's the same density, if it has twice the radius, remember the density is mass divided by the volume, and the volume is 4/3 pi r cubed. So if I keep the same density, right, if I double the radius, then the volume is going to be times 8, times 2 cubed, right? So if I do this times 8, and the density is the same, this is constant, then in order to have the same density, because the volume is now 8 times bigger, the mass has to be 8 times bigger as well, right? Because the density is constant. So the ratio would be 1. So then we know the mass is times 8. Now on this side, it's going to be times 8 on the numerator and times 4 on the denominator because it's 2 squared here. Remember that proportional reasoning, right? So ultimately, it's going to be twice as much, 2 times as much. You can do that more symbolically if you like, but that's the fastest way to do that proportional reasoning. Okay, so remember, try to think through all of the steps there and follow that along if that was a little confusing.